Welcome everyone to our October virtual star party. Tonight we'll be talking all about the James Webb Space Telescope. We'll get started here in just a few minutes. We're going to let everybody join us here as people are rolling in. I'm so glad you're all spending your time here on Friday night with us. If you have questions that you've already thought about of the James Webb, please put them in the Q&A box. We'll get to as many questions as we can tonight. And as we go on tonight, if you have new questions that occur to you, please feel free to put those in the Q&A box as well. So to kick us off, I do want to acknowledge that here as a museum, we aim to advance our collective understanding of both the Earth and the sky. And I would like to acknowledge that the Bell Museum sits on the traditional treaty lands of the Dakota people. I would also like to acknowledge the Ojibwe people, traditional keepers of the lands to our north. Dakota and Ojibwe knowledge systems are crucial ways of knowing this place now called Minnesota. And we at the Bell honor that knowledge, the values embedded in it, and the people who keep it. Now, questions are our favorite part of the night, so please do use that Q&A box, that feature in Zoom, to send us your questions and comments throughout the evening. We'll get to as many as we can live, and our team is behind the scenes monitoring those questions, so if we can't get to it live, we will definitely get to it in text. This event is being live captioned, so if you find those captions distracting or not useful, you can always hide them by clicking on the Live CC button on your screen. But to continue going, I am Sarah. I am the Planetarium Programs Coordinator here at the Bell Museum, located in St. Paul, Minnesota. And up on our roof deck tonight, hoping that the sky gets a little bit clearer than it was earlier today, is our planetarium educator, Tad. Want to say hi, Tad? So you might have to speak to have you see us on camera. I'm sharing my screen right now.
Yeah, it would help if I unmuted myself there. You think I would have known this by now? Just trying to light myself up here. Hi, everyone. I'm up on the deck. If you are here in St. Paul, in the Twin Cities, it's pretty cloudy, but I think we'll have some views of the moon as we go along here. If you're outside the Twin Cities where it's a nice clear sky, I'm jealous. Don't tell me.
And it is starting to get into that cooler weather. While Tad is up on a roof deck bundled up for observing, actually the cooler weather helps us out a little bit. It stabilizes the air. So just as we move into later fall and winter, the air will be more stable and better for observing. We have to bundle up. And by we, I mean Tad, who's up there on the roof deck. But let's see what we're going to do tonight. Later on in the evening, we are going to do an activity with that involves the Space Telescope here tonight. If you want to follow along with us as we do this activity later on, you will need a few things. You will need printouts that are of the sun shield and of the golden mirror. And we'll put these links in the chat so that you have them all. You will also need some string, a toilet paper tube, scissors, and some tape. If you want to follow along later, those are the things that you will need to do the activity with us. Otherwise, we'll put the activity in the link, or the link of the activity in the chat, and you can always do these at home on your own time. But that's just to give you a heads up of a cool thing we're going to do later. Now, as we keep going, let's take a look at our night sky, our star map, a very useful tool to help us pick out what we want to see when the clouds go away. You can find this link on our website. We'll also put this in the chat for you. But as we're looking at our map here for October, it is good for early October here around 8 p.m. And then as the month goes on, the same map and the stars will be in the same position closer to 7 o'clock in the evening. So let's take a look at our map and figure out what we can see tonight, or at least if the clouds go away. If you take a look here, you will see that our map is a circle. And that's because the edges of our map here mark out the horizon. If you were to stand in one spot outside and look in a direction and spin around in place and look all around, your vision, your line of sight would trace out a circle along the horizon. So that was what gives us our circular map here. Well, if the edges of the map are our horizon, the center of our map is the zenith, the point directly above our heads. Now, that is not where the North Star is, though. The North Star will be in a different spot depending on what latitude you're at. Here in Minnesota, we are at latitude 45. Actually, the museum is just a few blocks north of the exact 45 latitude mark. We actually have a plaque that's a few blocks north of us that marks the exact halfway point between the North Pole and the equator. So on our map here, we'll see high overhead, kind of right in the center of our map tonight, is one of my favorite things. It's the summer triangle. Well, it's not summer anymore. These stars are out in our early fall skies for a little bit longer. And so that's what will be marked by the bright stars Deneb, Vega, and Altair right there at the center of our map. Very close here, kind of running through this triangle of stars, we have this gray streak going across from like the northeast down to the southwest. And that is our Milky Way galaxy. That's not something we can see here in the Twin Cities with all our light pollution. But if you were to get away from the city lights and out in a nice clear dark sky, you could see the Milky Way stretching across our sky from northeast to southwest this time of year. A few other things you can see on our map tonight. We have a few planets in our sky. And tonight, when the moon is out, or when the moon's out from behind the clouds, I should say, nearby, just to the west of the moon tonight, will be Jupiter and Saturn. So kind of down in our southeast of the map here. Now, we don't have the moon on this map because the moon moves quite a lot each night. But Jupiter and Saturn, we're going to start in the southeast here in October. And as the year goes on, we're actually going to keep Jupiter and Saturn in our evening skies well into the end of the calendar year. But across the months between now and the end of December, they're going to slightly shift and move over to the southwest as the months continue. But they're bright enough and easy to spot. You do not need a telescope. You do not need binoculars to see these two bright planets in our evening sky this fall. Some other things to kind of take a look at here in our fall sky. The bigger the circle on the stars here on the map, the brighter the star will be. The smaller the dot on the map, the dimmer the star will appear from in our sky. But if you look just off to the east of our star map from that summer triangle that's kind of in the center there, you see the Great Square of Pegasus. And that's another fun, relatively easy to see shape in the sky to help you kind of navigate what's out in the night. Now, if you do have any questions along the way, please do remember to put those in the Q&A box. If you have any questions about what you've seen in the sky or where to find certain things, we can definitely come back to this map. But we have that link in the chat if you want to download the map for yourself and take it out with you. That's super handy. I keep one at my desk. But we are here tonight to talk about the James Webb Space Telescope. Now, the James Webb Space Telescope is really cool, and it safely made its way to its launch country, I should say. So let's see what it took to get the James Webb from here in the US packaged up and on its way. So the Webb is one of the biggest telescopes ever made. And so it did arrive this week, actually. It got shipped off and it took about 16 days at sea to go from California to French Guiana here. And it arrived on Monday. So it is actually shipping from, or it's going to be launching from South America, not from here in the US. It's launching this December. So this is a launch date. It's been long anticipated. And it's one that we are super excited to follow. And they've been doing a lot of testing and making sure everything works just right. And it's actually been launching from an Ariane 5 rocket, which is supplied by the European Space Agency. So this is not just a project that NASA has done. It is a or international collaboration to get this very, very big, very powerful telescope out into space. You may be wondering, why are we putting these telescopes into space in the first place? Because this isn't the first one that we've done. We have launched several telescopes. Spitzer was launched in 2003, and that looks at infrared light. Chandra was launched in 99, looking at X-rays, and that one is still operational. And I'm sure we've all heard of the Hubble Space Telescope. That one has been operating for over 30 years. And that is the one that gives us our beautiful pictures, much like the one behind me and many of the ones that you've probably seen throughout the years. So the James Webb is going to be that next great space observatory. Though it's going to do a lot what Hubble can do, but even more and in a slightly different area of light. It is the largest, most powerful, and complex telescope that's out there. Oh, and it looks like we have a nice shot of the moon between the clouds. So let's go.
We do. I hate to interrupt, but we've got to jump on it while we can here. And we have a quick look at our moon here as the clouds are coming over it. But it's a really beautiful phase of the moon. We're a few days past first quarter. So if you can get outside, again, if you're here in St. Paul area, come run outside and go look for it. And clouds are also kind of being annoying with the exposure. We are tilted in this view, so the camera is twisted a bit. That is turned relative to what we see. And a very bright moon here. But we can pick out those Maria, those darker patches there very nicely. Chrysia, I believe that's Mare Chrysium on what we see is the very top here of the moon. But if you're going outside to look at it, that should be on the right side of it, as we see it right now from here on Earth. Just gonna keep playing with the controls here to try to get it into view. I'll try out auto. It wasn't working too well earlier, but maybe it might help us work out tonight. But those Maria are nicely joined by the highlands of the moon. So those dark patches we can see joined by those lighter highlands, which are the young areas on the moon's surface, or excuse me, the older areas on the moon's surface. The Maria are actually the relatively younger ones, since they formed from impact craters after the moon formed, whereas those bright highlands have been relatively unchanged. Well, not with those large scale changes since the moon formed. And look at that. Okay. Well, we got a brief look at the moon. I seen that. You're welcome, Jeff there. You're welcome, Jeff. Hopefully it will come back here. If you do get a chance to go outside and look for it, I've also been spotting it like for a second or so, looking at the moon, and then up to the right of the moon, if you see a bright point of light, that will be the planet Jupiter. No promises on Jupiter tonight, just because the clouds have been moving over it every time I get a chance to see it, and I'm not sure I can get the telescope there in time, but well, no promises, but fingers crossed, right? Hey,
yeah, no, thank you for jumping in, because when you get the clearing in the sky, we do want to take advantage of that, because we are here to see live telescope views, as long as the weather cooperates.
Which sometimes it does.
Which sometimes it does. So we'll be hearing from Tad every now and then as he jumps in with a view, or if he just has something cool to share with us about James Webb here. Okay, well, it looks like we're losing the moon due to the clouds. One of the questions that just came in is talking about how does Hubble and Webb compare to each other? Well, here's a picture that we can see that Webb is actually a lot larger than the Hubble Space Telescope. So the Hubble Space Telescope, by comparison, is about the size of a school bus. James Webb, though, is about the size of a tennis court. So Webb is much, much larger. However, as you see here, it's not just that golden mirror that is so large. It's actually the sun shield, that kind of multi-sided diamond, if you will, around the telescope. And we'll talk a little bit more of that as we go tonight, both about the really cool engineering that went behind James Webb, but also some of the science that it will do once it's out in space. One of the things that it's going to be different than Hubble is that Hubble looks in visible light. So very similar to the range that our eyes can see, and a little bit beyond what our human eyes can't see. But James Webb here is going to be looking at infrared light. So I have a question for all of you. I'm going to put up a poll on the screen here, and I want to know what you think infrared light is used for. Is it used for night vision goggles? Is it used for sending TV remote signals? Checking for energy efficiency and heat leaks through doors and windows? Or is it seeing through clouds of gas and dust to find new stars and planets? Or is it possibly all of the above? What can infrared or IR light be used for? So I think that the electromagnetic spectrum is wonderful. It encompasses visible light, but infrared light down to microwaves and radio waves, all the way up to the higher end of X-rays and gamma rays. It's kind of like one of the Swiss Army knives of astronomy. There's so much cool things that we can see in space. We just have to use the right way to detect them. And that's why Webb here will help us see in a region a little bit larger than what Hubble can see. So it's going to kind of complement Hubble, but take us even further into what we can see and what we can detect here. So it's going to allow us to do a lot of really cool things. I will leave the poll up for just a few more seconds if you're still thinking on what maybe you've noticed infrared light being used for, or if you've ever heard of it before, or if you just want to take a guess if you've never heard of it. Okay, let's see. It looks like we're almost all on the same page there, that actually every single one of these things is an example of how infrared light can be used. So you actually are using it when you're using remote controls. A lot of the remote controls send infrared light signals. And the fun thing is infrared light can do some things that visible light cannot do. For instance, I think it's fun at home if I have my remote under my blanket so that my remote cannot see my TV in visible light, but I can still hit my remote buttons and the volume still goes up or the channel still changes. And that's infrared light, which can pass through that blanket. So it's kind of fun just to experiment with what can infrared light go through with the easy tool that many of us already have, is a TV remote control. Okay, but let's see what James Webb is going to do with this. Visible light. Here is an example of some meerkats and a freshwater crocodile using visible light. But if we were to use infrared, like Webb is going to do, they're going to appear different. These are that heat-seeking goggles. Or if you ever stepped in front of a heat camera or an IR camera, you see that warm-blooded animals, such as humans, are going to be quite warm, and we're going to glow brighter, like the meerkats here. But then when we get into reptiles and cold-blooded creatures, you can see the freshwater crocodile is a little bit warmer than maybe the greenery around him, but not much, because they're not generating the internal heat like mammals do. And so infrared is actually seeking heat. And so that's one of the reasons why we cannot put this telescope on the ground. Oh, question here, clarification. What is TV? Your TV in your house, thing that you watch your videos on, or you plug your computer into to stream Netflix or anything like that. Yeah, so it's just your remote control talking to your TV. It's not a science acronym by any means. But if I ever use an acronym nobody knows, doesn't know what I'm talking about, please do clarify or ask me to clarify. So because the Webb telescope is going to be looking for heat coming from distant objects in space, we cannot put it here on Earth, because the heat that the Earth is generating, the heat that the Earth absorbs from the sun, would actually interfere with anything it's trying to do and trying to see far out in outer space. And so what we actually have to do is we have to launch it pretty far from Earth, all the way out to this point called the Lagrange 2 point, or the L2 point, where the gravity between the Earth and the sun and the Webb will kind of balance itself out. So it's a fairly stable orbit out there, but it's not going to sit at just at one point. It's going to actually kind of create a little halo. It's going to orbit around that L2 point as it's out in space. And it's this far away from Earth, so that way we don't interfere with what it's trying to observe. But being in space and still being on the inner part of our solar system, the sun is still going to be an issue. And so one of the great challenges or the great engineering strides that they made is to create this sun shield. So if we look on the right half of our screen here, we see the side of the telescope that's going to be facing the sun. And this is where a lot of the electronics are going to be. But we have our solar power array. We have some antennas so that it can talk back to Earth and send us the data and send us the images. But on the other side of the sun shield, we see that there are 5 layers of the sun shield. And what that's going to be doing is it's going to be keeping the heat on the sun facing side. And so the differences in temperature between the sun facing side and the observing side are going to be hundreds of degrees. So that way the telescope and the mirror and what we're trying to see on the observing side, kind of the left-hand view of this image, is not going to be interfered with by the sun or the Earth or even the moon. So it's quite just these thin layers of the sun shield are going to do all this protection for the telescope, so we can see just the faint heat coming from distant planets. But it's not going to be launched into space in the tennis-sized court arrangement that it will take these measurements in. It actually has to be launched in a rocket, and then it will take about 6 months to unfold. And so here is kind of a snapshot of each of the steps that it will take to unfold. But what we can do is we can actually watch to see how this is going to happen, or how we hope it's going to happen, it's been designed to happen here. There is no sound to this, by the way. So then down comes the sun shield. And once both sides are down, it's going to start to stretch out. This whole process is going to take at least a month. From launch to the time it's going to be out at its location, it's going to take about 6 months. So this is a very slow process. And the reason we want this to be a very slow process is because this is very thin layers. And we want to make sure each step goes well, so that way it doesn't break. And because the Webb is going to be so far away from the Earth, if something doesn't work right, or something breaks on launch or on deployment, we cannot go out and fix it. So if you are an adult, you may have heard that when Hubble was first launched in the 90s, its mirror had a big issue. The mirror wasn't ground correctly. And so essentially we had to go to Hubble and repair it. And we've done that with some software updates, but also some new technology that was installed. But Hubble is close enough to the Earth where the astronauts during the space shuttle era were able to go to Hubble and fix it. James Webb here is going to be way too far away for anybody to go to it once it's launched. So once it is launched into space here at the end of this year, it is on its own. It is going to have to do everything as we programmed it, as NASA programmed it to do, without any interference from us humans on the ground. Question came in from Joey. Will it be able to capture data while unfolding? So it's not going to be capturing, let's say, images from stars or galaxies while it's unfolding, but it will be taking kind of measure of itself. And did this unfolding step work properly? And it will be sending that information back to us. And so that way, if something doesn't unfold right, we will know about it. So we can kind of see, is this something that just a software patch? We can just upload a software patch to it, or is it something more mechanical that we cannot help if it is mechanical? So it'll be collecting data, but just not the scientific data that it is intended to do once it's at its L2 point and fully deployed. What is the Webb telescope made of, and will it be visible from Earth? So 2 great questions. I'll start with the first one of what is it made out of. So each of these mirrors here is quite large. If you look behind me, actually, this here is a 2-scale model of just one of these mirror segments. And so Webb is made up of 18 of these hexagon segments that fit together. If we look on the right side of the screen here, we can see it in its folded up position, where we have that main set of maybe 3 columns of the hexagons, but then the other 2 are folded behind it, so that way it'll fit into the rocket. Once it's out in position, those 2 outer rows or columns of mirrors will actually kind of unfold, and it'll look more like we see in the center image here. Now, the mirror is covered in gold, actually. So it's not like the mirror you have in your bathroom that is glass with maybe some silver or some aluminum on the back of it to give it that reflective surface. The reflective surface of Webb does in fact use gold. And this thing is huge. So the one behind me here, and I'm sitting down, is about 4¼ feet tall from flat edge to flat edge. And from point to point of one of these mirror segments, it's just under 5 feet. Now, the entire gold here used for this entire mirror for all 18 segments is only about the size of a golf ball. And so it's really not that much gold at all. And the reason we have to use gold is because we are looking for that infrared light, that heat coming from deep space objects. And it reflects better and can be captured more accurately by using gold as that reflective surface. The second part of the question, I'm going to have to look at it again. I forgot what it was. I'll come back. Will it be visible from Earth? Yes, this is one question that I was just actually talking to somebody here at the Bell Museum the other day about. Now, it is quite large in space, and even though it's going to be further away from Earth than the moon, it might be visible. I couldn't quite find a definitive answer because I was talking it through with somebody. And on that sun-facing side, or the sun shield side that does face the sun and the Earth, it's large enough and maybe reflective enough that we might be able to catch it every now and then. Because that sun-facing side will always be facing the Earth. So we're never going to see this gold side of the mirror. That gold side has to stay pointed away from the Earth and away from the sun. But so I don't actually have a definitive answer for you there, because possibly, and it would be super awesome to see if it is visible through using a pair of binoculars or a telescope in our sky, if it does reflect that much of sunlight back to us. But stay tuned. We're going to see if we can keep digging and find some answers as this telescope gets deployed. Okay. So what is another question from Marco comes in? What is the first observation it is scheduled to do after it is fully deployed? So the first light it's going to collect and take images of, it's kind of a very ceremonious time in telescopes, but that first light is going to come in around August. So it's going to launch here in December, and after it unfolds, it gets to its location, it's going to start collecting images and collecting its scientific data around the time of August. So that's going to be a really exciting time. What those first images are going to be like, I don't know. But there are plenty of researchers across the world who have submitted proposals to use this telescope to help them advance their research. And Webb is actually a really interesting telescope in the fact that it's not going to have one camera on it. It's going to have several. So upstairs on our roof deck, and maybe if the clouds clear away, Tad will pop in and he'll show us one image of something through the telescope, because we have a telescope upstairs with one camera on it. Now, Webb here, they've done a really interesting thing, is they've tacked multiple cameras on it. So you can have one researcher looking at one area of the sky, but a different area slightly nearby is still visible to another camera. And that way, another set of research questions could be collected, or the data for those questions can be collected. So there's multiple cameras on this telescope. I don't know which order those projects will come back in, but we did talk to Dr. Michael Ratowski last night. And he is one of the researchers. He's actually stationed down in Minnesota State University, Mankato, and he has been awarded time with the James Webb in both the first round, so round 0, if you will, and the first full round of the telescope. It looks like Tad here has another view of the moon for us.
I did. Well, as soon as you're like, oh, we can get a view, it disappeared. It's kind of coming back there. The telescope's drifting a little bit too. We'll bounce it up here. All right, there we go. Really coming in. Oh, and you know what? I can see Jupiter too. Oh, I can see Jupiter and Saturn. You know, sir, I'm gonna try. I'm gonna push our left. It's nice and clear overhead, of course. I just noticed how clear it is overhead. I'm gonna see if we can try to get Jupiter into view. Of course, the clouds are coming overhead as I say that, but at least we do have a nice view here and there of our beautiful moon too.
Okay, well, we'll stay tuned and keep an eye on that telescope camera for us. But yeah, so there's an example of one telescope with one camera. We are not nearly as fancy as the James Webb is going to be here.
Hey, though, if someone gave me $10 billion, I could do something pretty cool too.
We could create some pretty cool telescope stuff on our Earth deck, no doubt about it. Okay, so a few other questions, which are great because we're still on kind of that engineering side of things. Why is the telescope being launched, not from Cape Canaveral? Why is it being launched from somewhere that's not the United States? Part of it, I don't remember the exact decision-making process. I read about it or when they decided that it's going to be launching from French Guiana, but this is an international project. And so the launch site is actually a European Space Agency launch site. It does have to be in South America, but the rocket is from the European Space Agency, and that's their contribution to this mission. And because a project of this size, both physically the size of it, the cost of it, but also the size of what it's going to do for us, could not be done by any one organization or one country. So it is truly an international effort, and that is where we utilized our partners for the launch here. But it's going to launch December 18th. It's already down there. It made it safely across and through the Panama Canal there. Now, if there's bad weather that day, it'll get pushed, but it is set to finally launch this year. And it's going to be really exciting coming up here in December. Let's see here. What do we have? The mirrors.
Sarah, if I can just jump in for 1 second.
Go for it.
Oh, just another reason we launch about that question about launch location. We the general scientific community, launching from the equator is a really good idea because you get an extra little push from the Earth. So the Earth is spinning around, and we're spinning towards the east, and that little extra push that you get down from being close to the equator, extra 100 miles per hour or whatever, helps just that little bit.
Okay. So yeah, so it is being launched from French Guiana, which is just north of Brazil. So it is going closer to the equator. I hadn't really thought about the Earth's rotation helping the launch of our telescope here, but that's a good insight there. Thank you, Tad. To take a look here of the size of the final mirror of Webb compared to Hubble, we have Hubble's mirror or primary mirror over on the left side of our screen, and so it's just a little bit taller in diameter than a person, but it is much smaller than James Webb once all those hexagons are stacked on top of each other. So each hexagon here is about the size of the one, it's exactly the size of the one behind me. Stands a little bit over 4 feet tall from flat edge to flat edge of each of these hexagons. From point to point of the hexagons, it's just about 5 feet across. And so each one of these 18 mirror segments is quite large. Now, the reason we need this mirror to be so big is because we want the pictures coming back, we want the data coming back to be as gorgeous and detailed as the pictures we've seen from Hubble for the past 30 years. Now, because Webb is going to be looking in the infrared part of the spectrum, the mirror to get that resolution to match Hubble's resolution needs to be bigger than Hubble's was, because Hubble's viewing mostly in the visible light. Webb here is going to be viewing in infrared. Okay, so we're going to take a break here from the engineering side of the telescope to go have some fun. Now, there's several fun at-home activities that we're going to put in the chat for you guys. You can do them on your own at any time. One of them that is particularly nice this time of year is actually some Webb pumpkin patterns. And so if you like to carve pumpkins, one of the links will give you several pumpkins to carve that go with the James Webb, maybe a spider web crossover.
Hey, Sarah,
Nice, Tad. Go for
I
it.
always hate to interrupt, but I also love to when we got a planet. So we have got a good view, actually, pretty good. Oh boy, look, the clouds are just clearing up nicely for us now. A good view of Jupiter here. So we are looking here at our largest planet in the solar system. And we've actually got some nice, I might play with the focus here in a second. We've got a nice view of the banding, these stripes that we're seeing. These are the stripes on Jupiter, which are in its atmosphere, which are caused by gas rising and falling. So this is a black and white camera, which gives us some extra sensitivity, but it does remove some of the beautiful colors. If you look up some images later of Jupiter, it's the darker, what we're seeing as darker stripes here are actually rather orangish in color. They're where gas is falling downwards into the atmosphere probably after being sort of changed, molecules changed by UV radiation. The lighter zones that we see are where that gas is initially rising up from the atmosphere. So these massive convective cells were overturning over and over. We don't have the great red spot tonight. I think we'll have a transit tomorrow night, but it looks like we don't have one tonight. If I super overexpose Jupiter, we can see some things around it though. I haven't gotten a chance to check which moons or exactly where which moons these are, but at least the spots we're seeing here go super bright. These are going to be the 4 or 3 at least of the Galilean moons. And oh, it looks like there might be another one down there. Those are also circles for those wondering what just appeared on screen. Actually, I don't know if I can actually do circles. I can do actual circles in Zoom. Boy, that would have been helpful to know 2 years ago. So what we're looking at here are 4 of the moons of Jupiter, 4 of the, I think we're up to 79 or 80 moons going around Jupiter. And these are the 4 largest, the Galilean moons. They were found by the astronomer Galileo. They're the first moons found outside of our Earth. So there was a momentous occasion in astronomy when this happened, because it gave some of this real great evidence that the Earth wasn't the center of everything, which would be the Copernican model, of course, that the Earth is not the center of everything. And then the idea that the Earth and all these objects are actually going and orbiting around the sun. Galileo was able to do this not by just looking at Jupiter once, but he actually kept track of Jupiter over weeks and months and years, and found their motions moved always with Jupiter. And it's a simple sight, but a really incredible connection, I think, to the history of astronomy and understanding our place in the universe. At the very least, understanding our place in the solar system. All right, Sarah, I'm going to try to, let's actually give one last view of Jupiter itself here. I'll bring the exposure back down. But I'm actually wondering, if the skies have cleared up enough that if maybe we might be able to get a look at Saturn, also known as the best planet in the solar system.
Yes, if we could get a view of that tonight, that would be fantastic. Kind of as we're getting this last glimpse of Jupiter here before we slide over to Saturn, one of the questions that came in is, will Webb be able to see different planets? And we're definitely going to dive more into the science here, kind of the second half of tonight here, coming up to it. But yes, Webb will be able to look at planets both in our solar system and out. Now, it won't be able to see all the planets in our solar system because, again, it always has to have that back side of it facing away from the sun. So it will never, ever see Mercury, Venus, or Earth. I don't know that it ever really will try to get to Mars because Mars is kind of close, but it might help us figure out more about like our outer gas planets. We haven't sent a spacecraft out to Uranus and Neptune since the 70s. Those are the Voyagers launched from Earth in the late 70s. It took them about 12 years to get all the way out to the outer 2 planets in our solar system. And that was the last time we've sent anything that far to those 2 outer planets. And so Webb might be able to help us learn more about some of our planets in our solar system, but it will definitely be looking for planets out of our solar system, looking for exoplanets, the formation of them, but also looking at planets we've discovered previously to help us figure out what are their atmospheres made out of, if they have any atmospheres to begin with. So Webb will definitely be looking at planets in and out of our solar system. And it looks like a success, Tad. Want to talk us through the favorite planet?
Yeah. All right. There's some clouds. Yeah. All right. There's some light clouds going over, so the view is shifting a bit here. And actually, sir, I need to just move around a little bit. I'm sort of kneeling by the telescope, and it's killing my knees up here. So 1 second.
So yeah, so Tad's upstairs at our scope, and it's a little chilly out there tonight. But thankfully the clouds are rolling away, and we can actually see a little bit more detail here than even Galileo saw with his telescope back when he was also looking at Jupiter's moons that Tad talked to us about. Now, through this black and white telescope, or this camera here through the telescope, we can actually see that differentiation from the rings from the actual planet. We have enough resolution to see the gap between the rings and the planet itself. Galileo didn't know what these things were, because back then they thought everything orbited the Earth, and they had no idea that planets could have their own moons or planets could have rings. So he called this a planet with ears back in the early 1600s.
And if I can jump in, one other thing he noticed as well, and it's something very cool. I haven't gotten a chance to see this myself, but Saturn is tilted relative to the sun, and that means it's tilted relative to the Earth. So sometimes when we see Saturn, we see it edge on, and the rings actually disappear. And this is noted by either, I want to say it was Galileo or Giovanni Cassini. He noticed this over years, the rings disappearing. And we have a record in his notes of asking, did Kronos eat his children? Which is, for you Greek and Roman mythology fans, I know you're out there, and I know you just gave a chuckle as well. All right, of course, the cloud. Oh boy, these clouds. I'll try to bump the exposure up as well. And, Sarah just saying these beautiful rings that are here. We didn't, we not really sort of know what was going on. We've had ideas for the longest time. And it was realized pretty early on that they couldn't just be one big solid object that would get destroyed pretty quickly by gravitational pulls, the gravitational pull of Saturn. And we now know, as the clouds come all the way over, that the rings are truly made of trillions of tiny little pieces of ice. So we found from spacecraft like the Cassini spacecraft right there that was going around Saturn for over a dozen years, that we have tons of little particles of ice. And we're seeing them from a billion miles away, though, or through the clouds. And that's why they appear as one big or two big objects. I think I'm going to have to call it on Saturn, at least for the moment here. Because
well,
clouds.
As Saturn kind of comes back in a little bit here, there was a question that came in, is why is Saturn the only planet with rings like this?
Well, there's a great qualifier on that. Like this, it is the only planet with rings like this. It is not the only planet with rings, though. We have found that Jupiter, Uranus, and Neptune all have rings. Saturn's, though, they are the most distinctive, and they're really the most distinctive because they're the youngest. The rings around those other gas giants probably formed billions of years ago around the formation of the planets, and they might be debris left over from the initial formation. But they've been around for so long that material has either fallen down and pulled down into those planets, or it's gotten very dusty, and so that it's very dark and very thin. Saturn's rings, though, when they're not covered by clouds, when we can see them, those rings are young. We think they probably formed sometime maybe like in the last 100 million years, which is like an eye blink ago. And they may have come, still some debate on this. I think the leading hypothesis, though, is still that they came from one or two large moons that got too close to Saturn, or got so close to Saturn that they were pulled apart by its gravitational pull. So there was this tug of war, essentially. Ooh, that didn't work. There was this tug of war going on, and those moons lost. Now, don't get me wrong, that is still continuing. That war of gravity is still going on, and the rings particles are falling into Saturn, so they're slowing down and falling into Saturn. They're also they get ionized by Saturn's magnetic field, and that slows them down as well. But in any case, they are disappearing. So if you want to see them, I would suggest, if you want to go with a telescope to see them, or get in a spaceship and go there yourself, you're going to have to hurry, because they're going to be gone in probably just the next 100 million years.
Question
That
about
is
these
some
rings. Another one.
quality astronomical humor right there.
I love them. Do the rings change their position relative to the planet?
Do they change their position relative to the planet? That's a good question. Not that I know of. That is, the rings are fairly stable in that plane that they're in. I wouldn't say that the particles generally, like overall, they go from, say, 20 degrees above or below. You know, they don't suddenly go like all the way up from like going up here or something. That is a horrible line. I'm so sorry, people. They don't go going. Boy, that is even worse. They don't change that dramatically. No.
So they're going to stay kind of orbiting around generally Saturn's equator. They're not going to all of a sudden change to orbiting the poles of Saturn, is what you're saying.
Yes, excellent. Thank you. I shouldn't try to answer and draw at the same time.
Okay.
So they wouldn't go like that. That would be super weird. That's a scientific phrase right there for you.
A question about what can we see tonight, that could we point the telescope tonight at Venus? Tonight, Venus, I believe, is already set below our horizon, but you can see Venus in the evening sky right as the sun is setting. Now, never, ever, ever look directly at the sun or too close to it either. But Venus is far enough away from the sun this fall to see it. It'll be one of the first things you see in the west as soon as the sun goes below the horizon. It's too late in the evening for us to aim our telescopes at it tonight, but definitely take a look next time we have a nice clear sky. You have the rest of the calendar year to step outside and look in the west to find it.
And there was that other question about, can we see the moons of Saturn? And I've circled one. They're very faint tonight, at least. Usually we get a slightly better view. So there's one moon, it looks like there's visible here. This is a very long exposure. We're doing a good 12-second exposure to try to get this. Couldn't tell you which moon. I would hazard a guess that that's probably Titan, the largest moon of Saturn, but the 5th largest moon in the solar system, right up there in the top. Oh, hey, look at that. Oh, that 10-second exposure, that helped us out. Let's see, let me draw in a few more circles here. I'm still gonna say the bright one's probably Titan. That makes the most sense to me. Other moons, we can see about 2 more here. Very faint. I realize there's another one down here. I'm seeing one over here. I may even just try for an even longer exposure, just to try it out. These will be other moons. Again, hazarding a guess this year, probably one Enceladus is probably there. Dione might be there as well. There is a great app. If any of you, if you have a smartphone, I don't know if those have reached out to everyone yet. I'm going to check it. There's a great app that I use. There's 2 of them, actually. One is called Moons of Jupiter. The other is called Moons of Saturn. And they both show you what moons of these planets are visible. It's amazing. It's just remarkably simple. And opening up on my side of things, it looks like, just sort of trying to match, of course, what we're seeing here on the screen. It looks like that is Titan there in the very top. I think it's, I think that's Titan in the very top. Dione and Tethys, I think, are the 2 that are very close together that I circled there. Oh, and I think that's Enceladus down right there at the bottom here. Shout out to my favorite moon in the solar system. That is Enceladus here. I won't try to type out its name. I'll let you look it up on your own. Enceladus is a small moon, a few hundred miles across, and it has an ocean underneath its surface. It is a water moon out there, which is incredibly exciting if you're interested in astrobiology at all. Which, Sarah, I don't know, I'm not sure if you've gotten a chance to talk about Webb and astrobiology yet, but it is an amazing moon. Finally rounding it out down there at the very bottom, it looks like we have a moon that starts, according to this app, it starts with the letter H, and I have no idea what moon that is. Sarah, do you know a moon of Saturn that starts with an H?
I do not. Saturn has quite a few moons. 83 last time I think I checked.
Oh yeah, we have. Oh, you haven't memorized them yet? Oh, I thought that was what we were all doing in our free time.
Nope. Some of them have very fun names, just not one that sticks to my brain. As we're looking at this, and we saw some moons around Jupiter as well, can you tell us what is the diameter of the telescope we're using tonight?
Yeah. So this is actually this is one of our smaller telescopes. It's a pretty easy one to set up though. That's why I grabbed it. It's a 102 millimeter, so 102 millimeters across. It's a refractor. So the lens is actually 102 millimeters, and it's by it's a company named Astrotech. So Astrotech 102 millimeter refractor. It is a fantastic telescope. It's one of my favorite telescopes. It's a grab and go telescope, because you can, well, you grab it and then you go.
It's definitely grown on me because I can one hand that telescope and mount it. So it is
Yes.
definitely grown on me to become one of my favorites as well.
And I'll just try to, ooh, I'm not sure if my camera came up. Hopefully it did. I think it did. Look at that. I'm right there.
I can see you. Yes.
There we go. So I'll just sort of turn around. We'll ruin the exposure we got going on there. So that is our setup here. I'll actually move around a little bit. Got a lot of cables. And hopefully we can see that. Siri will tell me how well we can see that. Maybe not at all. But that's our little telescope there. It's amazing.
And it looks
And
like we
that's
can see
our
the
camera on
moon,
the
the bright moon up in the corner of the sky as well.
Okay, yeah. And then for those who've been watching that cloud cam, if it's been visible, that has just been a little Canon, this is a Canon T6 with a fisheye lens, and that has been giving us our nice view of the clouds for most of the evening, although it's actually getting pretty nice out here, although it's still very chilly.
Okay. One last question about planets for now, and if they clouds keep behaving and allowing us to view them, I'd love to keep looking at them. But will Venus and Jupiter have a conjunction this year? Last year, December of 2020, Jupiter and Saturn had a very famous conjunction. You wanted to tell us what to look for later this fall?
Yeah, that's a good question. I don't know. Well, Jupiter and Venus, I suspect they might. I wouldn't be super surprised. Venus is going to be visible throughout the new year, but Jupiter is moving closer to the horizon, or it's slowly setting as we go along. We passed opposition about a month ago. So yeah, I could imagine in a couple months we might have a conjunction. I will have to double check that one though.
And thinking about how the planets move across the sky throughout the months, Jupiter and Saturn are definitely getting close to Venus by the end of this calendar year. I don't know if they'll be close enough to be considered a conjunction that we can see at night, but they're definitely going to get closer as we get to the end of 2021. If I'm remembering my planet positions correctly.
That seems about right.
Okay. Let's see. The request came in, if the clouds clear up, if it's possible to see Europa, if we ever go back to Jupiter tonight. But I'm going to take the screen back because I want to kind of do a fun hands-on.
You can. So someone actually read my mind. Maybe let me quickly give a view at least of. Look at that. The spot on. Yeah. Sorry to just take over again here. We're back to Jupiter. We can see the moons there. I'm going to break out that great app, Moons of Jupiter. And we have coming down from the top. Look at that. Europa is right there at the top. I'll circle them one by one. I won't try to write the names. That's going to be Europa up there. We have Io over here. And then we have going down, we have Ganymede over here. And then way down here, we have Callisto. So down at the bottom there is that fourth Galilean moon, still very large, still about the size of our moon. But little Callisto way out there, the most heavily cratered object in the solar system. Callisto is incredible. But that first one, Europa, I'm guessing someone is a fan. I didn't see the question. But I'm guessing someone is also maybe a fan of water, or maybe 2001: A Space Odyssey, who knows? And Europa also has an ocean. It's another water, it turns out, is incredibly common. Most of it's frozen because the universe is cold. But there's a lot of liquid water out there in space. And that has been, I think, maybe the most exciting discovery, like on a big scale, the most exciting discovery because of what that means for the potential for life. And I'm just gonna, sir, if you want to take your screen back, I think, I actually think the camera needs to be, I think the camera needs some percussive maintenance right now to get it working.
Okay. As we switch away from the telescope live views here, there's one more question that came in about, does Jupiter affect Earth's orbit? The planets all have our own stable orbits. Jupiter does act like kind of a big brother of the solar system, though, where it will collect incoming asteroids or other debris. So it doesn't go into the inner solar system. So it's kind of a fun thing to think about, is Jupiter being some of the protector of the inner planets by capturing some of that debris or shooting it out of its way, or kind of adjusting incoming debris trajectory so it doesn't really impact the inner solar system.
Although at the same time, it probably does shift stuff around, so it does move into the inner solar system. So,
So the gravity of Jupiter is quite large, so yes, it probably does more than just one thing. Okay. So if you earlier when we first started, if you grabbed your materials, we're going to do some fun at-home activities. We'll put some links in the chat to more of them. One of them is creating pumpkins and pumpkin carvings. It is that Halloween time of year here. To marry spider webs with the James Webb is just one of the fun patterns they have. But if you gathered your materials, we are going to try our hand at packing our own space telescope. So again, what you'll need is a printout of the mirror, a printout of the sun shield, some scissors to cut them out, some string, tape, and a toilet paper tube. So the patterns are in the link that we sent. So if you didn't print them out now, you're welcome to follow that link and print them out when you have a moment here. But what we have to do is we have to figure out if our toilet paper tube here is kind of the fairing of our rocket. So the telescope has to go in here, but our mirror is too big to go in as is. We've already talked about how Webb will kind of fold up to fit into the fairing of the rocket. But your challenge now is to figure out how to get the sun shield and the mirror together, folded into the fairing, and then able to come out of it with just the string and unfold all on its own. So I'm going to try some things here. If you're following along with me, maybe you'll find a different folding pattern or a different way to attach your strings. That's kind of the fun part about engineering, is you try something, and if it didn't quite work the way you want, you try something else, and you keep going until you find a solution that really fits what you need to do. So I got my sun shield and my mirror attached, and so I'm going to fold this up here. I'm going to try some things. I'm going to attach my string kind of to the middle. See if this helps. Attach my other string. We're going to attach to the other side. Okay. And I'm thinking, now that I'm already doing this, I'm thinking I put my string maybe not in the easiest spots. I think I attached it too close into my mirror. Let's see if this helps. So now I'm going to see attempt one goes in my rocket fairing. So now if this is what's getting into space, if I were to just pull on these strings, will my telescope unfold? Now there's no gravity in space, so I can't shake it out. But if it were, it didn't quite unfold all the way. So my James Webb folding technique could use some improvements. I'm thinking I put my strings in the wrong spot, but this is kind of what you could figure out, is how could you get it to fold and fit in your rocket fairing and then unfold just by pulling on those strings. Maybe it's the position of the strings. Maybe it's how many strings are pulling it out. This is just one of the very engineering marvels that Webb had to figure out. And people had been designing Webb, and the first idea of Webb happened before Hubble even launched in the 90s. And so this telescope has been in the making for quite some time, and it's now ready for launch this December. Okay, so I changed the position of my strings. Let's see if it works any better. That worked a little bit better, I would say. Still not perfect because it still come out of the tube very nicely. I had to kind of jiggle it a little bit, and again, there's no gravity in space to pull that tube fairing out, but there'll be kind of some help with getting out of the fairing as things drop away from the telescope. So hopefully your telescope, Paca Space Telescope, maybe worked a little bit smoother than mine. If not, keep trying. Okay, now on to the fun science here. We've talked a lot about the engineering and what it's going to be doing and how it's going to be doing it, but what is it going to be doing once it does finally get out to that Lagrange 2 point? What is it going to be looking for? And it has many different things that it will be doing, but pretty much it comes down to these 4 categories. Webb is going to help us study the early universe. It's going to look at galaxies as they develop over time. It's going to help us study the life cycles of stars. And it's going to find other worlds and help us study other worlds and the atmospheres to see if life could exist on any of them, or just what other planets are like. Because right now we only have the Earth as our example for life. And there's plenty of other planets out there. The number just went up today from the last time I checked. We're over 4,530 planets out there now that we know about. But Webb is specializing in the infrared part of our spectrum. So this is light of all different wavelengths. We can see here kind of on the left part of our spectrum here, Hubble is really focused in on that visible light. It goes a little bit into the infrared and does a little bit over into the ultraviolet, but Hubble specializes really in that visible area of the spectrum. And then here, kind of in the middle of the 3 telescopes, we have the James Webb. It has a very broad region covering infrared. It'll go from near infrared, very close to that red light of visible, and down to about mid infrared here. And so Webb is going to have quite a span of wavelengths it's going to be looking for. And then even further down to kind of capture that far infrared, that's where the Spitzer Space Telescope came in. Spitzer was retired in 2020, but we still have that wonderful data from that telescope here in the infrared as well. But how is it going to do those 4 scientific areas? So one of the things it's going to be doing is trying to figure out the early universe. What was it like in the very early universe back 13.8 billion years ago? Because back then, stars just started forming and the gas around them kind of started heating up. And that's on this left side of our image. Over time, stars assembled into galaxies. And then galaxies became more massive. And then we see the clear universe, kind of where we see a little bit better images of the galaxies near us today. And so actually, the closer a galaxy is to our own, the closer in time we're looking at it. So when we look at, let's say, the moon tonight, the moon is close enough to the Earth that it only takes light about a second and a half to get from the moon to our eyes here on Earth. But when we were looking at Jupiter through their telescope not too long ago, Jupiter being farther away, it takes light an hour to reflect off of Jupiter and come to our eyes. So we weren't actually looking at Jupiter as it was, 5-10 minutes ago. We were looking at Jupiter as it was an hour and 10 minutes ago, because it does take time for that light to travel to our eyes across space. When we look at the Andromeda Galaxy, which is even further away, and it's actually in a pretty good spot here this fall in the constellation of Andromeda. That galaxy is 2.5 million light years away. So when you look at that little smudge in the sky tonight, or on the next clear sky night, you're not looking at that galaxy as it is right this moment here in 2021. You're actually looking at light that left that galaxy 2.5 million years ago. So the further away a galaxy is, actually the further back in time we are looking. And so Webb is going to help us look back beyond just our close galaxies, back to the very early galaxies, see what were they like way back when. And then that'll help us answer the question of, how do galaxies evolve? How do they get here in this kind of succession or a flip book of galaxies? How did they get from that little red dot over on the far right of our image, that very, very distant galaxy as we're looking back in time by billions of years? How did it get through all these stages as these galaxies are progressively closer to our own, and we can see more recent pictures of them and figure out, how did galaxies progress through this kind of transition? Did they transition? And so galaxy evolution is still a question that we have. How do they do it? What do they evolve from, and what do they evolve into? It's still a big question, and we have some ideas, but Hub is going to help us uncover more answers to that question. But Webb is actually going to help us peer through and actually examine the dust itself. So this kind of gets back to my TV remote example from earlier in the evening of what infrared light is used for. Visible light, kind of like the image on the left here, can see the gas and dust. And in here, this one is the pillars that we have in space. But visible light cannot pass through gas and dust, just like it cannot pass through that blanket as you're cuddled on the couch with your remote control under the blanket. But infrared light can. So just like when you hit the volume on your remote and it passes through that blanket, no problem, and the TV volume changes, infrared light can see through these pillars in this middle image. And so we can start to see how the pillars almost seem to disappear into these. And we can see all the stars hiding behind all this dust. Now, on the far side of this image is a mid-IR image from Spitzer. So Spitzer did retire, and Spitzer is going to be a lot smaller than Webb. What Webb is going to help us do is not only see near infrared, kind of like this middle image that was taken by Hubble, but it's going to take this mid-infrared light that's on this far right side of our image. And that image from Spitzer really doesn't have, it's not really high resolution anymore compared to what we're used to. But Webb, being so large, is going to take that Spitzer image in that infrared light. It's going to look at that same area of the sky, and it's going to return high resolution images just like we see on the Hubble on the left two images. So because Webb is so much larger, it's going to be able to see the dust itself, but then also examine what's happening through and behind that dust in very good resolution, very high resolution images here that we're used to from Hubble. And so by using this, we are going to look through that gas and dust to see how do stars form? How do they live their lives? And then how do they die? Because stars do die in many different ways, depending on how massive they are at birth. Stars like our own sun are an average size star. They're not all that big, actually. And so what our sun will do when it runs out of fuel is it's going to kind of swell up like a giant balloon. It's going to puff out those outer layers, and it's going to leave behind the core, which we will call a white dwarf. But when the stars like that puff out those outer layers will form gorgeous planetary nebulas. More massive stars than our sun can potentially explode in supernova explosions. They can leave behind neutron stars, pulsars, and if they're massive enough, they might even leave behind black holes. And so Webb is going to help us study the life cycle of stars here. And we mentioned a little bit ago, it is definitely going to help us look at planets. And so here is an example of an image of finding planets orbiting a different star. So in this image here, the star itself is so bright that we've blocked it out. That's kind of that black circular disc in the middle of that image. We put a little five-pointed star where that star would be. But once you black out or kind of mask out the star itself, the not quite as bright objects start to appear around it. And this again is why we're looking at infrared light, the faint heat from planets and not the bright, intense energy coming from the stars themselves. So in this image here, we can see 3 different planets orbiting this star that we've blocked out. And so Webb will help us find these planets, but then it also start to help us figure out those atmospheres. It'll take a look at the spectra of them, what colors are still visible, what colors are absorbed, or what wavelengths of light are absorbed. And by using the spectra of these planets, of the atmospheres coming through, we can see what are they made out of, what components are in there. Is it oxygen? Is it methane? Is it carbon dioxide? Do they have, my lights are going off on me. Does it have an atmosphere anyways? And if it sees oxygen, maybe something there is living. Methane is another good indicator if there's life on a planet as well, if it does find methane on any planets. And it will re-examine our planets in our own solar system. But again, the planets outside of the Earth. So it will not see any of those planets that are closer to the sun than we are, again, because Webb has to be kept at very cold temperatures so it can see that infrared light. So it will not be able to see Mercury, Venus, the Earth, the moon, or the sun itself, but it could be used to point outwards to Mars and beyond. Okay, so we have several questions coming in, and it looks like we have another view of Jupiter. Take it away, Tad.
Yeah, well, I thought maybe you might want a second to turn your lights on. Yeah, so boy, we had a gap in the clouds, and then it just disappeared. All right. Well, I was trying to get us all a view of Jupiter back. The moon is coming in out of view, but I was still on Jupiter. And that was just an image we just saw. That was an image released not too long ago, the past year or so, of Jupiter, tracking heat in Jupiter's atmosphere, actually showing us these same things we're seeing here, those stripes and bands, the belts and zones, as we call them, belts and zones. And let me try to answer some of these questions. Sarah's been talking so much. Let me try and answer some questions. We had a great one there. Can James Webb Telescope uncover extraterrestrial intelligence? Probably not, in the sense that if there's someone out there talking to us, every telescope on Earth would probably be able to detect it. I think what it's really gonna be able to do, though, is get us a better handle on whether or not there are possible sources of that there are possible gases and elements out there that could be produced, maybe be produced by biotic life. So what was being talked about a little while ago, stuff like carbon dioxide or oxygen. These are things that living things here on Earth produce, and it's possible that an abundance of them in the atmosphere of another world could be evidence of life. Not a direct detection of life, but maybe some indirect evidence that, ooh, we should really pay attention to that world. There's another question I saw there about funding for space and astronomy, and I think my answer to that would be no. For that person who asked that, I think it's good. Question's gone now. What technique enables astronomers to measure how far the infrared light has traveled from its origin to reach Earth? That is a great question, Brian. The big way we do it, at least when it comes to Webb and studying galaxies, we are measuring how much the light has shifted due to the expansion of space. This is known as cosmological redshift, or just redshift if you look that up. And what we'll be doing is we'll be looking for specific elements, that is, or rather we're looking from light coming from specific elements, and we're seeing how much that has shifted. And the amount of that shift tells us how far that galaxy has receded away from us, and that gives us its distance. But if you look up cosmological redshift, I might ask Megan if you're out there to type that one in, that word cosmological. But that will give some more information as well about how we measure that distance. But yeah, measuring how far that light has stretched over time. Coming quickly back to our view here, bit of a gap. Well, there's some cloudy haze there, so we got a little fuzzy view. That motion that we're seeing here, if you want some evidence that it's live, besides me zooming in and out, that motion we're seeing is actually the motion of our atmosphere. So that's all these water molecules in our atmosphere and our clouds, and they're distorting our view. A phrase in astronomy generally known as seeing. So I'd say tonight we have pretty bad seeing. We have a lot of motion in the atmosphere. This is one good reason why you'd want to go put a telescope up in space where you're very far away from the atmosphere, where you don't get all this junk cluttering your view. And of course, if you're measuring something like infrared light, again, like Webb is doing, then you want to be very far away from these sources of infrared radiation, which is one of those reasons it's really the reason it's so far away from the Earth. I'll bring back the view for those who've been here or those who've just joined us. See if we can bring back a view of some of the moons as well. And I'll try to get a picture here again and I might try to get these posted on our Facebook page later. One of the great things about the Galilean moons is that they move around the planet relatively quickly. That is, Io, the closest moon there to Jupiter, goes around it in about a week. Callisto, furthest one away, takes about 3 weeks or so to go around. Someone out there, feel free to double check me on those numbers. But that means that on a given night, we can sometimes actually see a lot of motion of these moons. We can actually see them in different places. In particular, Io, which if I recall correctly, is going to be this little spot of light right there. That is the smallest moon. That one, usually you can see a good little bit of motion of over half an hour or so. Especially over the course of a full night. And it's a moon that you can also see very often coming out from behind or in front of Jupiter. So when we look at Jupiter, we don't always see all 4 of these moons because they're moving around. Sometimes they're in front of Jupiter and Jupiter's light is, outshining them, or they're behind Jupiter and Jupiter's like blocking our view. But that means that sometimes we get 3 moons, maybe 4 moons, maybe just 2 if you're sort of at the right or wrong time, depending on how you look at it. Io is the fastest mover there. Does that change quite easily or quickly though. Looks like the clouds are coming over again, so I'm really bumping up the exposure here to several seconds there, and there's all those moons come out. We've also got Callisto way down there. That was one I was trying to see. And we've either got something over there, which I'm gonna guess is probably a hot pixel on our camera. It looks a little too perfect to be a moon, to be an astronomical object. So that's probably just a little error here in our sensor frame.
Tad, a question came in.
Yeah.
So you were talking about how the light redshifts. So that's how we can figure out its distance. Now, that light that it's coming back from us, a little follow-up on that. Do they know the actual colors of the things we'll be seeing in the images coming back from Webb? Or do they have to guess as to what the colors are they believe them to be?
Oh, the easy question for me. Thank you, Sarah. So that is a complicated question, and I'm going to give you a complicated answer. Well, no, hopefully not too complicated. So when scientists receive this data, first of all, when they receive information in the infrared, it doesn't have a color. It's not what we can see. We can't see infrared light. So that pure infrared light doesn't have a color, but our camera sensors detect it as some level of energy. So we see it as we're seeing this view of Jupiter here in front of us. We're seeing it essentially in black and white. White where our camera sensor is measuring something, and black where it's not measuring something. Now that black and white image, then we can add colors to it, and we can do that in a couple different ways. One is we can just take some different colors, whatever colors we want, and we can add them to it, and we'll use different colors to represent different things. So for example, we might color code a black and white image so that where there's more energy, we're going to color code it blue. And where there's less energy, we'll color code it red. And then we'll have this gradient, this change from red and blue. Now, again, is that really the color there? No, there was no color there, but it's giving us a way to understand it. Going back to what I said, though, again, about how we're measuring the distance is we're looking for specific elements. And we're measuring something like hydrogen. We're measuring hydrogen alpha. Hydrogen alpha is a very specific wavelength of light. And by looking at how much it's shifted, we can tell the distance. But if hydrogen alpha is shifted in the infrared, well, that's great. We know that we can see hydrogen alpha in the visible light when it's not rapidly moving away from us. So hydrogen alpha is actually this really beautiful red color. It's like this purest red. If you look it up, it's absolutely incredible. So what we could do is we could take that black and white hydrogen alpha image, and we know, quote unquote, know that when we see it, it would be red. So we make it red. And that's still the color of hydrogen, just again, not the color we were picking up. So that was a very long answer. And if you're super confused by that, please, I was gonna say, I don't think we have the chat open, but if you want to follow up with that in the Q&A, go right ahead. I'd love to talk more about this. There's a real amount of art that goes into coloring images that we see of space. Colors are never randomly chosen. They're always do relate in some way to what we're seeing and helping us understand and make sense of what we're seeing, even if the color may not actually be there in whatever way.
Okay.
All right, so
well,
I got the hard question. Maybe there's an easy one for you, Sarah.
well, if anybody does have any more questions, please do send them in the Q&A box. We do just have a few last minutes left here together tonight. But there's a few other things coming up that I want to make you all aware of as we get to enjoy some more live views through our telescope up on our roof deck. And if any questions come in. The first thing is actually tomorrow. Tomorrow is International Observe the Moon Night. And so this is a program where
it should be clear tomorrow night too. It should be clear. So
we might actually have a chance of seeing it. But yeah, so tomorrow is International Observe the Moon Night. So this is a night because we only have one moon here on Earth, and it's always out the same day for everybody around the globe. And so we can all go out and appreciate that we are looking at the same object in the sky, and really kind of create that community sense of looking up at the same object as somebody right next to us, but also as somebody who might be in a different state or even a different country, to kind of get that global community going and appreciating our own only natural satellite that we have, the moon. So many places will be having celebrations for it or having some more astronomy programming. So you can always take a look in your area to see if any of your local astronomy clubs are celebrating tomorrow night's International Observe the Moon Night. And then in next month, ooh, there we go. Nice view there. We're getting a close up of the moon. And then next month, we'll be having another virtual star party, talking more.
Sarah, I just want to check, can you hear me? Because I can't, I lost my audio over here. So if you can hear me, just give me a thumbs up and I'm going to assume I just lost. Okay.
My microphone was just telling me it was acting up. Sorry about that, guys. I hope you can hear me now.
Oh, I can hear you. I can hear you now.
Okay, so that was a tech issue on my end. Sorry about that.
Okay.
So what I was saying, and I'm not quite sure when my mic decided to go out on me, was that tomorrow night is International Observe the Moon Night. So that is an opportunity for people in your local neighborhood, but also across the country and internationally, to observe our moon and really appreciate our own natural satellite. So if you're interested, and Tad was saying that tomorrow night will be a clear night, or it should be a clear night here in Minnesota at least.
Okay, don't hold me to that. I mean, if it's not clear, don't.
Weather is, nobody actually knows what the weather is going to do. But if it is clear out, definitely take advantage of the time. Go outside, observe the moon just with your eyes. You have a pair of binoculars. It could be a pair of birding binoculars. Go out and use that to see some of these details that Tad's showing us right now. But it's an opportunity for us to really appreciate our only natural satellite, and that everybody across the globe is actually really looking at the same moon at the same time, or the same moon and the same day, that is. So we do share this common view of our night sky. And then next month, our virtual star party is going to be on Friday, November 19th, and it's going to start at 7 p.m. So it's gonna be a little bit earlier in the evening than we started tonight, just because we're gonna take advantage of the sun setting earlier and earlier as we get to the winter solstice. But next month, we are gonna be focusing here on the moon, and specifically the Artemis 1 mission that's gonna be launching hopefully early next year, 22. I do think it got pushed back to 2022. But the Artemis 1 is going to be an uncrewed mission as we get ready to send the first woman and the first person of color to the moon here by the year 2024. And so we'll be focusing on that mission coming up, because it is going to be a really historic event as we get those people to the moon for the first time in over 50 years. Any last words for us, Tad, on the moon that you have us looking at?
Oh, well, I mean, it's the moon. What I'm trying to see here, if we can get, I really early on, I said I was going to turn the camera around, so it was north up, and I never got around to that. So I'm sort of twisting my head here to look at it. I was trying to see if we could really pick out Tycho crater. Is this actually, oh boy, my moon geography is just the worst sometimes. We've got some beautiful rays down here, so I'm trying to make sense of what we're seeing. And we've got some rays coming out from down here. So is this south? You know, that picture I shared, well, I might have had the directions wrong. So we know that's Chrysium up there. Boy, just keeps getting, you know, I mean, at least the moon is coming out from behind the clouds there. All right. Ooh, those. Boy. All right. Sorry. It's hard to talk and do this at the same time.
Yep. No, it looks kind of like it's backwards and mirrored to me, if I'm remembering the position of the moon as I see it with my eyes. So I believe down kind of, if we look to the lower left of the corner of the image along the terminator, I believe that's south. Yep. So I think Tycho actually might be just on the, still not quite visible to us.
Okay. Yeah. So yeah, those should be yeah, that's right. Yeah. Yeah. Thank you. Boy, these clouds. Well, I'll just try auto exposure here. So what I was trying to look for at least were these rays coming out from it. So there are these streaks coming out from Tycho. It's a really young crater on the surface of the moon. Young here is astronomically speaking for those who are here who are watching when we had Saturn. This is within the same time frame, well within the last 100 million years. Which one way we can tell is from the fact that the rays are still there. As micrometeorites hit the surface of the moon, features slowly do wear away, they weather away. But that does take tens of millions of years. We've also got, yeah, a very nice, is that, I want to say that maybe Copernicus crater down here. I'll have to double check my names though. The big one, we can see rays as well coming out from that. So we have some very intricate craters on the moon. That's one of the amazing things here, especially if we get even closer. I don't know why I wasn't doing this earlier. That's the surface of the moon. It is super cool. We've got these incredibly intricate craters. One amazing thing here we see as we go inwards is this really cool central peak that's sticking up here. There's actually sort of the multiple peaks. And understanding lunar crater formation is like a PhD thesis in its own. Luckily, some people have already done the work. And we know that there's this really complex thing that happens when an asteroid or this rock strikes the moon, it smashes down into the surface. And then the energy, it goes downwards, but then it also rebounds back upwards. And these shock waves go in and out, or out and in, excuse me. And it forces this central peak upwards in some craters, depending on the angle. And then it also leaves us with this really massive wall structure around it. Of course, the sort of what we think of as the crater itself. And then early on, of course, in the moon's history, when this happened, that gave us the Maria, those large seas on the moon, because that also released lava from below. So all these large dark areas are, again, these massive, let's click there, these massive impact craters. But even these smaller ones are visible. You know, the big ones that we can see here, the craters, you know, those are going to be about 60 miles across, but as we look closer and closer, we can see smaller ones that are just going to be, you know, a couple miles across. We're also seeing here a lot, this sort of one here that in front of us, as we look in the screen here, you know, it's sort of this half bright white, half dark. So we're seeing sunlight coming over the edge of the moon. It's hitting that crater wall, which is slightly higher there in perspective to the sunlight. So it's all nice and bright and lit up, but then the other interior part of the crater is in shadow. And these are, again, horrible drawings on Zoom. So every time we look at the moon, you know, I want you to go out and look at it tomorrow night. If you have a camera, use a camera, look at it with your own eyes, whatever. It's all great. It's all great to look at the moon. There is ever-changing detail on it. There are features that are visible, in fact, only roughly about an hour or so throughout the moon's phases, because it depends exactly on the sunlight hitting the surface. So things, in fact, that we see kind of over here on the surface of the moon, just coming to view on the Terminator, these lines, if we can pick them out here, I'll try to draw again on the Zoom screen here. These lines are going along here. If I've got it right, these are some probably, well, it could be a variety of things, actually. One thing that we could be looking at here are lava tubes, collapsed lava tubes. So where lava flowed across the surface and then cooled down, or excuse me, flowed under the surface and cooled down. And we end up with these tunnels. They could also be rills, which is where the moon's surface is actually moving around. We know the moon is still active now. We did measure moonquakes going back to the Apollo program. We have evidence of that. But it used to be a lot more active early on when it was still very warm inside. So that could be some evidence there that we're seeing of some of that movement on the surface. This has been shortly, of course, after sometime after the Maria formed. We've got these are actually the edges of a crater wall here. Sorry, I keep misclicking. This whole long stretch that we see here. Sarah, I realize I'm just talking through our time here. But
Okay, well, I'm going to take the screen back because we'll go deeper into this next.
Massive crater wall. All right.
But take a look at some of those details tomorrow night and enjoy International Observe the Moon Night. Go outside, take your neighbors, talk to somebody who lives in the next town over you, and really appreciate that it is a global event to appreciate our moon that we all share. Again, we hope to see you back here next month for our November virtual star party, which will be focusing on Artemis. And we'll definitely talk more about the moon, where we're going, why we're going, and different features that are there. And what we hope to discover when humans go back to our moon. And I want to thank you all for joining us tonight. Astronomy programs like this are made possible by Ruth and John Huss and the generosity of donors like you. So thank you all for joining us for our October star party and talking all about the James Webb. We hope to see you back here next month. Have a good night, everyone.
Have a good night, everyone. Stay safe and stay warm.